Thank you. So we're recording from now. Okay, so just to kind of recap here for the interest of this, we've been speaking about establishing the resting membrane potential. The first thing we described is the sodium-potassium pump that is creating this environment, right? It's pumping sodium out, 3 sodiums out, 2 potassiums in. That's going to be 20% of what we see as the resting membrane potential directly owed to this pump. And then the remaining 80% is due to the environment that's indirectly created by this pump as well. The fact that we now have more potassium inside the cell, more sodium on the outside of the cell. And so these ions can now leak according to those gradients using these ion channels. The second thing we described is the relative permeabilities, right? We have more potassium channels, creating more of an opportunity for potassium to leave, and fewer sodium channels, creating less of an opportunity for sodium to enter. And those two factors together, the pump channel, the sodium-potassium pump, in coordination with the leak channels and the differing permeabilities of those leak channels, now creates this negative environment inside the cell and a positive environment on the outside of the cell. Okay, and what we're describing now are the forces acting on our ions separately. So we talked about the CDF of sodium, right, which is really influenced by sodium equilibrium potential, positive 60. We talked about the EDF of sodium, influenced by the membrane potential. We're then now speaking about the CDF of potassium, which is influenced by potassium's equilibrium potential, and the EDF of potassium, which is again influenced by the membrane permeability of -70. And now the next step here, the fifth step, is to really combine these forces and talk about the ECDF. Okay, so the ECDF is going to be the combined forces acting on both ions. So if we consider sodium, sodium is pretty straightforward, right? We have sodium acting forces acting in both directions, into the cell according to the CDF, also into the cell according to its EDF. So if you combine those two values, remember, if we have two forces, we simply add the values and then the general direction will follow. So sodium will have a strong ECDF into the cell. And the value or the magnitude of that ECDF will be just combining these two values. So that'll be 130 millivolts, okay? Which means, kind of simply put, that sodium really wants to get into the cell, right? Really strong force there. If we think about potassium on the other end, again, we're gonna combine our, we're not gonna combine our forces, excuse me. We are going to consider our algorithm, right? Because the forces are acting in opposite directions, we now have to think about which of these is the bigger value. So this is where we consult the equilibrium potential and compare that to the membrane potential. And because the equilibrium potential is the bigger value, the general direction of this ion will favor the CDF, the chemical driving force, excuse me, okay? Again, according to what we said in our algorithm there. So potassium is going to have a force that is going to be weak because we're now going to subtract that 70, that -70 from -94. So it's going to be a weaker value, but its general direction will favor the chemical driving force because this is the bigger value. All right, so it's going to have a weak force out of the cell. And again, in terms of putting a value here, we simply subtract -70 from -94, and that gives us -24, millivolts. All right. And kind of a simple way to put that is potassium doesn't really want to get out of the cell. It's kind of like trickling out of the cell. So sodium really wants to get into the cell, really strong value in terms of its combined ECDF. Potassium is kind of just trickling out of the cell according to its weaker ECDF. But we now want to also think about the differing permeabilities. So because sodium really wants to get in, but it has less channels to do so, and potassium trickles out, but it has more channels to do so. This creates this balancing of the inflow of sodium with the outflow of potassium. Okay, and this is how we get to that steady state, and we no longer see accumulation of these ions on either end. Okay, so we now arrive at steady state. And we maintain that -70. Okay. So this is how we establish that resting membrane potential. And this is why at rest, a neuron is more negatively charged inside and more positively charged outside. And as we describe this, we're going to build on this conversation and talk about how we can use this knowledge, this understanding to excite this neuron, right? We will eventually speak about the differing permeabilities. So we can basically make the inside of this neuron become more charged, more positive, more excited, simply by opening up more different types of sodium channels. So we'll talk about other types of sodium channels that are not leak channels that can then manipulate the membrane potential and therefore excite the cell, which is called an action potential, right? So the basis of understanding this is to build upon this and then speak about how we can excite this cell and generate an action potential. Okay. I hope that was clear. I'm going to pause a bit for any questions.
Are there other ions that can go inside the cell aside from sodium and potassium?
There are, yes, excellent question. There are, so I want you to keep remembering that because we'll speak about them later on. There's calcium that can move inside the cell. It's higher concentration outside, it's going to move in. There's chloride at a higher concentration inside the cell. So we have other ions that are moving. We have hydrogen ions. We've got a lot of other ions. And so what we're speaking about now is only sodium and potassium because they are the most influential on this -70 value.
Okay.
Okay. Yeah.
That makes sense.
All right, so let's keep going here. Now there is a video, a really nice kind of summary video that I've pasted in Brightspace that you should be able to see that kind of simplifies this. So be sure to check this out as you're reviewing this to kind of see this in a 3D type of way. So the final thing that we'll say here as far as this packet is how this understanding of what's happening in a cell at rest is the basis for the conversation of what happens to a cell when it's excited, okay? This is called an action potential. This is a brief period of extreme electrical activity or an extreme electrical impulse that facilitates the excitability of cells, especially neurons, muscle cells, cardiac muscle cells, skeletal muscle cells. They have the ability to be excited and generate this action potential. So we've spoken about how we get this -70, and the same principles are going to hold true as we speak about how we go from -70 to -55 and eventually to +30, okay? So that's what we're going to move on to speak about, how we can then think about those same principles and use them to discuss how we can excite a resting cell, okay? So I'll just kind of briefly describe here. We're comparing the membrane potential on the left to time. And so these are the events of a single action potential. We go from the resting state, we go to -55, which is our threshold value. And I'll describe what threshold means later on coming up. We then depolarize this cell. So this rapid influx of ions approaching +30 millivolts is responsible for the upstroke or the main event of the action potential. After that, we're then going to try to approach our resting state once again. And so we repolarize the membrane by moving another ion, and that will bring us back down to our resting membrane potential. Now, can anyone think of our two ions, sodium and potassium, given the understanding that they're moving in order to approach their equilibrium potential, which of our two ions do you think is responsible for phase one? This rapid positive change in the membrane potential. Which of our two ions would be moving to create this type of membrane potential change?
Would it be potassium?
So it's not potassium. Remember, potassium has an equilibrium potential of -94. So if potassium were trying to move to approach its equilibrium potential, it would be leaving the cell, creating a negative environment so that that membrane potential would get to -94, right? And so by default, it's going to be our other ion, right? It's going to be sodium. So as sodium moves, remember, sodium is it's moving to approach its equilibrium potential, which is +60. And so as it moves, the membrane potential would become more and more positive. As it comes into the cell, it's positively charged. It's going to create a positive membrane potential change in an attempt to approach its equilibrium potential. And so potassium is going to be the opposite movement. It's going to be movement that results in phase two or repolarization. So when we get to this upstroke of the action potential, we're going to have a reverse of those ion movements. So potassium is going to now move. Remember, potassium's movement is out of the cell. It's a positively charged ion. And so as it leaves the cell, it creates more of that negative membrane potential change. And so as it tries to approach its equilibrium potential, which is -94, so way down here, it's going to be leaving the cell. We're going to see that negative membrane potential change, and then we're eventually going to see the resolution of that potential change back to our -70, which is our resting membrane potential. Okay, so just generally understanding what we've said so far about the movement of sodium, the fact that it's moving in an attempt to approach its equilibrium value, which is really positive for sodium. It's going to be moving into the cell to do so. And the same is true for potassium. It's moving in an attempt to approach its equilibrium value, which is way on the other end of the spectrum, really negative. And so it's going to be rushing out of the cell, not rushing, but trickling out of the cell in order to approach that value, which will result in a negative membrane potential change. Okay.